Hello students, we will come to part 3 of critical regionalism in Indian architecture, and today we will start with the case study of what I believe to be one of the finest apartment buildings ever built in India. And trust me, I have seen quite a lot of modern Indian architecture in my studies, and I have rarely seen a building of the quality and the study material that I can derive from the Kanchanjanga apartments in Mumbai by Charles Correa in 1983. Tell you the truth, if an architect were to design only this one building in his lifetime, only this one building, he would be well known. Charles Correa designed many such buildings. That is why he is considered to be one of the greatest modern Indian architects. Now there is one more thing I would like to tell you. And let me make that point by coming to the elevations of the building. The Kanchanjanga apartment was a high-rise apartment building with condominium of 32 luxury apartments, 4 different types of them from 3 to 6 bedrooms each. It was a pioneering exercise in bioclimatic design. It was also a brutalist inspired building paying homage or a salute to Corbusier. Now the evolution itself. So you take the block, a cuboid, and you start developing the cutouts in that, and the cutouts, the big loggias and the small loggias all start coming together in the final form. The point I want to make is here, the site plan and elevations. Let's look at the elevations. All 4 elevations speak to us differently. They are a tremendous exercise in composition. Each of them is a very simple cuboid. Each of them has a set of cutouts based on the side or the orientation of that particular part or that particular elevation, and responding to that, the sun path in that particular or responding to that particular orientation. This picture shows you how the building appears from the southwestern side, the southeastern side, the northeastern side, the northwestern side. These are the 4 facades: the south, west, north and east. Now why is it important? If I were to design an apartment block today, much of my apartment block would have a very similar language more or less all around it. Maybe the variation would come because I would have balconies on a certain side, maybe I would have a closed wall on the other side. Much of it would be unremarkable, and to tell you the truth, much of the apartment block construction today is unremarkable. It does appeal to you because of the kind of finishes that are being used or some kind of aesthetic elements that are being used, but when you draw closer to the building, the warmth that you feel when you study Kanchanjanga, it's amazing. It's, again I will repeat the same word I used last time, it's a master class in understanding modern Indian architecture. Does it have flaws? Of course, all buildings have flaws in them, but today we will focus on what we learn from this building. There is one more thing. Architects, or rather I don't say architects, I say that this is something of a thought, that the creative process fundamentally is opposite to the scientific process, that the creative process is fundamentally against or opposite to the scientific process, and in a sense that's true. A scientist, that is a technologist, is a doctor or an engineer, has not much to do with creativity in his work. His work is that there is a problem and the solution has to be found. The artist on the other hand has very little to do with logic. If a painter is making a painting or a poet is writing a poem, there is called a poetic license or an artistic liberty that he has. He can paint the sky purple, he can paint the sky violet, if he is able to define the idea that he is trying to give to us. It is fairly subjective. The technologist's work or the engineer or the scientist's work is objective. It can be quantified, this cannot be quantified. It can be evaluated numerically. This work, the creative artistic work, cannot be evaluated creatively. But the architect is not just a creative person. The architect is also a scientist and an engineer. The closest an architect comes to in the world of creativity, scientific, the closest he comes to is a craftsman, a carpenter. A carpenter is a craftsman. For example, when he designs a chair, he has to keep in mind that the chair has structural stability, otherwise nobody would sit on it. I mean, anyone sits on it, it will collapse. But it has to be attractive also, otherwise nobody would want to sit on it. So those both things, the artistic part and the scientific part, come together in the work of a carpenter. Of course, a carpenter would generally be doing it more intuitively. He would have learned the craft from maybe a series of generations before him, and he would have understood the basic rules of load distribution, etc., more empirically, more through experience. Whereas because of the very magnitude of the building, an architect has to learn that as a student scientifically in your structural classrooms, because you cannot do this intuitively. Of course, there is one segment that you need to also understand load distribution intuitively to generally understand a building if you want to do it in a prelim form, just in as quickly as possible to understand. That is, of course, this is a part that is necessary, that you have to have intuitive understanding, but you have to have a scientific understanding also. What am I trying to say here? These scientific constraints of a project, climatic constraints for example, are a set of scientific constraints, have actually led to very innovative and beautiful architectural solutions, but where the constraints have been fed to the wind and have not been taken care of, solutions have been very generic and unremarkable. Science actually, what I am trying to make a point is, science actually leads to a more interesting, aesthetically pleasing, better building than non-science. This is a fact. It may not be that the scientific part of design of Kanchanjanga is right in front of you, it's right, like it's well documented. No, of course not. Because at that time, like I said, it was more experiential, it was more empirical, it was more based on the understanding of a local climate and then building around it. But still, in a sense, it was scientific, because that data of the climate had to be used to create the building. Okay, if you still don't agree with me, look at some of the best buildings being made today by architectural firms like Morphogenesis or the firm of Rajrival, etc. Amazing buildings which are strongly rooted either in strong structural data or strong climatic data. No doubt about it. Hall of Nations is such a beautiful project simply because it's such an innovative structural project. The STC building by Rajrival is such an amazing project because it is a Vyrindal girder that has been used in such an interesting way. It's a structural innovation that leads to such a remarkable building. Let me continue further. Let us see the comparison between Kanchanjanga and United Habitation designed by Le Corbusier in France, and the complex spatial organization of both the buildings. If you look at United Habitation, it is basically two sets of apartments, or rather two 1.5 apartments, one full floor and one half floor. In this manner, they are plugged into the building. So therefore, they become one on top of the other. They come together like this, and this part is the corridor in between them, and therefore they both have complete glass access, a complete fenestration access on either one of the two sides. And so here is the picture showing this plugging in of the apartment into the structural grid of United Habitation. Now Charles Correa adopted the same idea in Kanchanjanga, of course with a little more complexity. The apartments again come together. This is one apartment and this is the other. But the amazing thing here, and of course even here, I am sorry, I did make a mistake here in trying to, it should have been more clear. This is how the apartment would come together. If I were to draw it again, this is how the apartments would come together. If this is your apartment, and then this is the next one on top of it, this is the way it is. And somewhere in between, I'm sorry, I'm missing out on the corridor part of it, but there's a corridor part of it in between. What I'm really saying is there are openings on both sides. There are fenestrations on both sides of unitary habitation. Now the same thing happens in Kanchanjanga. There are fenestrations on both sides. There are this is the section of unitary habitation. As you can see, yeah, okay. Now this is I should have referred to it in the beginning only. This is one apartment. Yeah, I'm sorry. Please forgive me for that mistake. So this is the other apartment, and this is the corridor in between, right? So there are fenestrations on either side and either side, and you have a double height space here and a double height space here, and similarly you have a double height space here and a double height space here. In the case of unitary habitation being made in France in a cold climate, the buildings were, the windows were enclosed from both sides, both glass, trying to bring in maximum amount of light and sun into the building. In the case of Kanchanjanga, hot and humid climate, they, instead of the double height space, actually became a terrace or an open veranda or an open balcony, and that became a big sit out that we will look at. So the Corbusier influence was Corbusier's response to the Mediterranean sun with the overhangs and the double heights in the unitary habitation, and Correa added the terrace in the double height space, which was possible because of the tropical conditions, and there was greater transparency through these large openings and terrace gardens on every floor. Every single apartment has these terraces, these private terraces or private verandas or private terrace gardens on every floor. Now what is bioclimatic design? That design of built-in spaces that is based on the local climate, and the aim is to provide thermal and visual comfort by plus making use of solar energy and other environmental sources. So if I were to take a section of a bioclimatic house, it would have the breeze flowing in through, it would have the use of the sunlight, use of proper shading devices, etc., etc. Use of, for example, this kind of ventilation, this kind of a louver vent here at the top to allow for the hot air to move out of the building. Or for example, this work by, I believe, Anupama Kundu in Auroville, and here again you find these louvers, these concrete louvers that are movable, and that help in controlling the microclimate or the indoor thermal comfort conditions of the space. The basic elements are passive systems for heating, cooling and lighting of buildings. Now there are some top rated green buildings. When I say bioclimatic design, I am primarily referring to what we call as green buildings today. So we have the CII Sohrabji Godrej Green Building in Hyderabad by Karan Grover. We have the TZ Homes in Bangalore in 2009. We have the Suzlon Complex by Christopher Benninger in 2009. We have this apartment, this Infinity Benchmark corporate building in Kolkata by Agarwal and Agarwal Architects in 2009. We have the Rajiv Gandhi International Airport in Hyderabad in 2008, and we have the ITC Green Center in Gurgaon in 2004. What do you find here? These are buildings spread all over the landscape of our country. Buildings in Hyderabad, in Kolkata, in Pune, and in Gurgaon, in Bangalore. Everywhere these bioclimatic responses are being done by architects who are making that extra effort to try to make their buildings energy efficient, climatically responsive. Let me also tell you one thing. This is not going to be an either or situation tomorrow. It is not going to be a matter of choice but a matter of necessity. You will be required to design energy efficient, carbon neutral buildings in the days to come. There will be a tremendous amount of push in every industry because we have to meet our targets of carbon neutrality. If Europe is targeting 2050, India is targeting 2070. Do not forget that there is also a sub-target India has to meet by 2030, and the sub-target is that we have to nearly bring down our carbon emissions by half by 2030. We are around 2.4, 2.5 billion tons carbon emissions per year. We are targeting to come down to about 1 billion tons by 2030. So it's not just the end goal at 2070, there's also the sub goal in between. Now these targets are going to be written in concrete from tomorrow. They'll be so strongly needed because we simply cannot afford to allow this kind of climate change and global warming that's going on. What is the code red? I may have talked to you earlier about it. Code red was mentioned a few months back when COP26 took place. I think just before that or just during that time, that if we exceed 1.5 degrees Celsius rise in temperature from pre-industrial levels, we will reach a situation which will lead to near irreversible climate change globally and global warming on an unprecedented scale. You've already seen the impacts, things that have never happened before, flooding in Frankfurt, droughts where there have never been droughts, melting of glaciers, rising of sea levels, a very genuine concern today. That which was only in people's minds few years back or few decades back, this might happen, sea levels will rise, islands will sink, is now becoming a reality. It is not something that will happen 30 years from today. It may happen 10 years from today, 5 years from today. So as an architect, one of the critical areas that you will be required to work in is energy efficiency and climate responsiveness. Of course, there are many other issues that are coming up because many other issues are becoming important. Resilience, mental resilience is becoming important. Universal access of buildings is becoming important. These are all scientific things. These are all scientific things. And the architect tomorrow will have to have a very strong scientific mindset. Of course, creativity has to be there, but please remember, as I'll keep on emphasizing this, please do not neglect these scientific subjects in your studies. In Mumbai, the optimal orientation is a built-in conflict. And what is the conflict? That to catch the prevailing breeze in this hot, humid climate of Mumbai, it is essential that we have the building orientation east-west. But east-west is also the right axis for the best views from the Arabian Sea on the west side and the harbour on the east side. But east-west is also the direction for the hot afternoon sun and the lashing monsoon rains of Mumbai. What is the intelligent solution? The intelligent solution, I believe, came up in the colonial times with what came to be known as the bungalow. Bungalow is coming from the word Bangla, and I believe it is coming from somewhere in the western regions of India, and or rather the eastern regions of India towards Bengal. And the idea was very simple. You have a house which has got this veranda running all around it, and as a consequence of that, all your living areas never get direct glare of the sun. It's completely cut off. This is the veranda and it's cut off. So now these living and dining spaces, for example, in this bungalow are in between. The bedrooms are on the periphery and then in fact the veranda is on the periphery. Now why treat the bedrooms in such a manner? I mean, true that the veranda would cut off the sun, but why have the living dining in the center and the bedrooms on the side? Very simple. Living dining are spaces that will be more used during the daytime when the sun would be at its peak. The bedrooms would be more used in the night time, and therefore keeping them on the outer side would allow for the night breeze to come in. The sun is not there at all. So as it is, the veranda is taking care of the glare of the sun. There's another addition that they've done. They provided the bathrooms on the other side that also cut the sun as much as possible and provide a defense against these elements. So now this kind of a configuration works well against the solar glare, it works well against the monsoon rains, it allows for maximum natural ventilation for the breeze to blow in through and through the house. These are some of the traditional Indian bungalows that we see. This of course is a modern derivation of a traditional bungalow. Now coming to the plan itself of the apartments of Kanchanjanga, we find the bungalow principle applied to this. Let us look at it. This is the ancillary space, the washrooms, or let's come to the lower level of this apartment. We've got a terrace garden here, we've got a servant's room, we've got a bathroom, then there are other facilities, and this is the interior of the building. Now we've got again these ancillary facilities on this side, and as a consequence of this, all your living spaces are within, right. You do get this diffused light from the terrace garden, and you do get light from other sources, but much of it is enclosed, and this wall is more or less blank with just this one small fenestration. So he is attempting to create the same bungalow principle in the apartment block. He does that in type C, he does that in type D. He is trying to keep the living spaces as protected as possible from the direct impact either of the monsoon rains or the glare of the sun, because this orientation like this, the east west is like this in this case. Now large outdoor spaces are provided with deep overhangs to protect the principal living spaces from the direct sun, and also to serve as wind catchers to enhance the natural ventilation. So what he has done is he has provided this double height space. That double height space in unit habitation was the living area of the house, the living room of the house. In this case it becomes an open space, a veranda, a sit out, and this is how the daylight filters into the house. I'm not saying glare, I'm saying the daylight, the diffused light, and then there is the action of the breeze within the house. And this entire volume, it also serves, like I said, as a wind catcher, capturing the wind and pushing it into the dwelling. And so when you look at the interiors, you find diffused lighting coming in the dining area, the living area, and the other spaces. The outdoor space then becomes a garden terrace or a terrace garden, which is a modern interpretation of the traditional Indian veranda. It's a double height veranda which has been taken out of the building corners. As a result of that, you get views on two sides, and the small balconies overlook the terrace because the house is duplex. So these balconies overlook the terrace. Not only it makes it a private space for the family, and it's not like your neighbors are on the floor above and they are looking down in a space that is your private space, but it is the same family unit and it is their space looking down into the bigger veranda, the sky veranda below, and thus creating this intimate domestic scale in the giant order of the building. No? So within the apartment, as you sit out in this space, even though you are high up in the apartment, you still have a feeling of this very intimate scale. Now there is another interesting variation of the bungalow principle, variation on the bungalow principle rather, and that is converting the veranda itself into a terrace garden. Now this did not really happen in the sense that the idea was conceptually seen by the architect, and that was that there would be a protection zone and a garden would be planted in this zone in the veranda space, not only because it protects the living area from the sun and the rain, but also because being this double height vast space, it would provide proper nourishment to the plants, adequate height for the garden zone, and such spaces in high rise housing are important because this makes the decisive difference between actually making a habitat that is livable or creating a claustrophobic environment that you do find today in these tall high rise apartments closely packed together. And then we come to one of the most interesting, remarkable buildings in modern Indian architecture, the Sanghat, the office of the architect B.B. Doshi from 79 to 81, grassy mounds with steps, terraces, water cascades, making it a beautiful, serene, harmonious environment with nature, and it is not the building that stands out as a remarkable form, but actually the building organically merges with the surrounding landscape. I am as if speaking the language of Francoid, right? And they are the earth hugging walls. The structure is predominantly subterranean, and it is covered with China mosaic chips on the top. So this is a subterranean building, as you can see. This is the section, and part of the building this much, it's underneath, it's cut into the earth, it's earth on both sides, and the barrel vault is on the outside. And then if you look at it's raised on a plinth and buried in the ground. We also find the same principle in the underground Shiva temple at Hampi, and we get that diffused light in the interior. So this is the Shiva temple at Hampi. This is the underground space that has been created in that temple, and here you find, you rise up the plinth, then you go down into the subterranean structure, and this is the studio in the subterranean structure, and the light is filtering in from the barrel vault, and it's a diffused light. Now I'm just deviating a little bit to come back to Sanghat and talk about right now the upcoming concept of blue-green infrastructure. I had to find a spot where I can bring this idea to you, because this is a contemporary idea that is being talked about in modern day urban design and planning, and in large scale projects. The blue-green infrastructure is a combination of blue, that is the water, and green, that is the vegetation components, versus the grey infrastructure of roads and settlements and canals. So extensive blue-green infrastructure or extensive blue-green components within the grey infrastructure lead to a healthier environment. So in urban planning, where there are water bodies and land which is interdependent, they grow with the help of each other while offering environmental as well as social benefits. The important objective of the blue-green infrastructure has been incorporated in the Master Plan of Delhi of 2041. Now, Doshi, at that time there was no such thing defined as blue-green infrastructure, but he empirically applied it. Like Charles Correa empirically applied the green roof in the MRF building, Doshi applied the blue-green infrastructure in Sanghat. It's a complex, the complex is a part of the landscape rather than the landscape being a part of the building or the building complex. The vegetation is in fact allowed to grow into a kind of a wilderness. It is not like properly demarcated and well aligned hedges, etc. There are dense trees in the west and the south, and the water is an integral part of the passive response. Water is, now this slide actually shows you different kinds of aesthetically beautiful look at water in projects in the Salk Institute by Louis Kahan, in the Mughal Sheraton, where the response was based on Mughal architecture, and then you find it here in Sanghat, where the water flows down the channel and it goes all the way, and it is then reclaimed. It's a part of the rainwater harvesting cycle. These are the water channel images of Sanghat, and the slide itself makes you want to visit Sanghat. It's such a beautiful building, so serene and so pleasant to look at. So here we have it. This is the plan of the building as you are approaching the building. Now there is something Japanese about this building, and what is that? You see, there was the classical processional approach in Greek architecture, in Roman architecture, that was also adopted by European architecture, and we found the reflection of that in modern architecture. But in Japanese gardens, the approach is different in that there is no processional approach. There is no bang big thing at the end of a road that leads to it. You are constantly drawing yourself towards that big image. But what is there is that it's a meandering pathway of a series of events, and you keep looking at that till you come to the end of your journey. So when you do enter the Sanghat, you assume that this is where the entrance is going to be, as you would assume naturally for any building. You come in and bang in front of you is the entrance. No, it's not, because you actually you actually have to deviate in this direction, go through the green area, climb up these open air theatre, these steps, and then enter the building from behind. And this is the way. I'm sorry, I need to place it better. I'm mistaking the pathway myself. You need to actually correctly visualize it, because here is the pathway in the model, and I believe that somewhere at the back you're entering into the building. So that is an amazing thing, that you do look at the building in front of you, but you don't enter it, you enter it somewhere from the back of the building. So the design of the Sanghat is a walled compound on a podium that descends in a series of terraces to a landscape garden here. So I climb down towards the garden from the building itself, and there's this long barrel vault that forms the backbone of this composition. Now these guest rooms are provided at the back, and there are several smaller workrooms that are under a pair of these raised vaults. So the guest rooms here, these are the raised vaults at the back. In fact, if you do get an opportunity, please look at pictures of the vault study that were done through some simple and crude models that were made for the Sanghat project. And this is how we see this this movement here. This is the grass amphitheater, which is also used sometimes for lectures and meetings and concerts. And then there is the reduction of the internal heat gain. Now if you watch very carefully this picture, this barrel vault that is being created, in the barrel vault there is one layer beneath. Over this, these elements, this terracotta elements are being placed, cylindrical terracotta tiles are being sandwiched between these thin ferrocement shells. Then after the ferrocement shells have been laid, they are covered with white ceramic broken tile pieces, as you can see here. They reflect the heat and thus reduce indoor heat gain. So the ceramic tiles do the job of reflection, but whatever is able to go through is then fended off by the air gap that is created because of these cylindrical terracotta tiles. So because they create that air gap in between the two layers of the ferrocement shells. Now this work of broken ceramic tiles is called as trincandis, and trincandis was first we find its major use in modern architecture by Antoni Gaudi in, for example, the Casa Batlló, a house that he did, or even in the Güell Park. This is the example of broken ceramic tiles, colored ceramic tiles being used in the trincandis there. Now the stack effect is also being created, a convection current is being generated in the workspace, and because of the vaulted form above. So there is an efficient surface to volume ratio which optimizes the quantity of materials that is used. This high space volume, like I said, is one of the important things we need to generate that convection current and the stack effect, and provides the hot air pockets that rise up and they move out from the openings in the barrel vault, and the cooler air moves in. So the daylighting in the interiors is diffused, it pulls in from the skylights that are there in the barrel vaults, and even there is a full window here. If you just go back, you see there is a full window here, it is pulling in the light, and the normal windows, they are punctured into the wall, and there is also this flat roof in which there are these glass bricks provided, and light filters in through this also, and over these glass bricks the falling water is passing. So daylight to the studios is without glare and heat. When we talk of the subterranean structure, we are also reminded of the Chaitya halls and the rock cut Chaitya halls, and here we have it. Because of the earth mass on either side, it creates natural insulation, but they have taken advantage of these thick external walls which are nearly 1 meter deep by hollowing them out and creating storage niches in them. So it is insulating as well as there is space efficiency through that. Now rainwater harvesting in cycle, this of course is a classic example of B.V. Doshi making the drawing of the building as a Rajasthani painting. As you can see, it lacks perspective, It doesn't have the feeling of depth in it, it's flattened out as it would be in a Rajasthani painting. Now the rainwater and the overflow of the pumped water from the roof tank is harnessed through these roof channels. It runs through these series of cascading tanks, goes on, and then through an underwater channel it comes into this pond here, and that is recycled back and it is used for irrigation of vegetation. Now please remember, this is a project in the beginning of the 1980s, ended up in 1981. The idea of rainwater harvesting as a necessary concept in buildings has really caught on in the 21st century when we are focusing on sustainability and green building design. In fact, it is one of the critical principles for green building design today, and in some cities you cannot have the building be passed without a proper rainwater harvesting mechanism, something that came organically to B.V. Doshi in Sanghat in the 1970s, late 70s, early 80s. And why? Simply because they were trying to make their buildings responsive to the climatic conditions. So when we now go to the India Habitat Center in New Delhi by Stein, if you just look at the climate responsiveness, this was done in 1993, it is again by non-mechanical means. Now the interesting part is that by this time economic liberalization had already happened in India. Of course the building began before the liberalization actually happened, but we were already in the throes of beginning to use active systems in our buildings, but India Habitat Center continued to depend on predominantly, at least in the courtyard planning, etc., the non-mechanical means dominating the building for climate control. To reduce solar heat gain, the buildings are placed around shaded courtyards, and the courtyard itself become ideal interactive spaces, something that was an accepted thing in traditional Indian architecture. The courtyards, the verandas automatically used to become spaces in the daytime during the hot sun where people would congregate together for a cup of tea or for a discussion. So the courtyard was an ideal interactive space. IHC, as many of you might have seen the pictures and many of you might have visited, is a typically modern building. It's a typically modern convention center, exhibition center, seminar center, but the overall space organization is so traditional. This massively beautiful courtyard, which many of you might have actually visited, is covered with this louver which is mechanically movable, and it generates amazingly interesting spaces within. There's amount of greenery used there, landscape elements used, and there's a completely pedestrian complex as all the traffic is diverted to the basement right from the entrance of the IHC. Now the green areas, we recover the lost green cover in this building by creating terrace gardens, by abundant use of planter boxes throughout the complex. On the ground level there are a number of garden courts in between the buildings, and there is also the concept of vertical hanging gardens. These elements, these planter boxes that you see, which is also found in the Fort Foundation building done by Stein, I have shown in the picture earlier. This idea of recovering lost green cover through terrace garden is again a fundamental principle of green building design, which was then done organically by Stein. And the pergolas, the courtyards are covered by pergolas suspended through a space frame structure. So the idea is coming from earlier, but now the technology being used is modern technology. There are 3 large sunscreen pergolas that contain these panels which are angled, and they block the summer sun and let in the winter sun, and the panels are made of sailcloth. Now if you see the isometric here, for example, there are variable shading of internal courtyards during the summers and the winters, and the pergolas, they shade the courtyards, they shade the inner facades of the buildings, and thus create a unique microclimate year in, year out. If you have visited, as I have had the fortune of visiting, the courtyard space, it is an amazing space. It has its own microclimate. You walk out of the hot sun of Delhi, you step into the courtyard, you step into another world altogether. These are some of the pergolas as they are being used in modern Indian architecture today, and the pergola, though being an idea that evolved much earlier, is now being used in our buildings in a completely new way with the kind of materials we have today. I will stop here. Thank you so much for joining me today, and we will continue with some more case studies, and we will try to look at other aspects also along with climate responsiveness as we continue to study one of the most important segments of Indian architecture, critical regionalism. Thank you.